All right, so the goal of this video is to go over AP Practice Problem 2, get the answers, and look at the criteria for getting all the points, and see how that's done and what they're looking for. All right, so in this problem, hopefully you remember when you read doing it, it's about researchers that are designing experiments compared to two different types of shoes. There's shoe A and shoe B. Basically, they want to minimize the time someone's doing a mile run. They want to minimize that. They do the experiment to two different kinds of people. One considers themselves a professional runner. The other is a recreational runner. So because there's a difference in the people, they decide to do a block design in their experiment. Remember, blocking just means, well, we have two different types of people, and we're afraid that those different types will affect the experiment. So we're going to separate them out. That way, differences in those people won't affect the experiment. Because we basically know there's different types of runners, so we don't want that interfering with the shoe results. They take 50 professional runners, 50 recreational runners, and they're each randomly assigned to wear one of the types of shoes. And remember, the randomization is the best way to sort of sift this out. And they're going to ask about why randomization is the best. But we've talked about it. You should at least realize that being random is the best thing to do when all things are all things being equal. And their running times will be recorded, and we'll see what happens. All right. So the first thing they ask is, what's the statistical advantage of blocking by the classification of runner? So I kind of already alluded to it. We don't want the type of runner affecting the results. We even have to be careful, because even if we were purely random, the problem is that when we're purely random, we may not evenly spread everyone out perfectly, right? So it is possible to randomly pick and get more of the professional runners maybe to be on have shoe A, and the recreational runners have shoe B. So if more professional runners are using shoe A, the problem is we don't know if shoe A is better because shoe A is better, or because shoe A is appearing better because people who are better runners are using it, right? So basically, blocking helps in preventing the difference in running speeds of the professional runners versus the recreational runners from interfering with the possible effects on the run times of the different shoes. So since the professional runners should be faster in general, it's basically important to separate them out, so we know that if there is an increase, we'll see it in both groups, right? So if we separate the runners into the professional and the recreational, and then split up the shoes within them, we'll be able to see the effects on the separate groups. So we'll be able to see, if shoe A is making both the recreational and the professional runners faster, we'll be able to tell that because we block them out. All right, so that's the importance, because basically we don't want one variable affecting the other. That's like when things get confounded, we don't want that. And since we know that there's that difference, we can, randomization helps with differences we don't know, but in this case we are aware of this difference, and it's good to make sure that we mitigate it before we do the experiment. The next part asks, why is it important to randomize the type of shoe the runner will wear instead of allowing the runner to choose the shoe? Well, the whole point of randomizing is, even though we could control the first thing, we knew there was the difference between the runners, we don't know everything about these people, right? There could be some other factor that we can't think of or we're not aware of, that if they choose the shoe, people who have a certain characteristic will choose a certain shoe, and that characteristic may not only make them choose a certain shoe, but may also make them a faster runner. So I'll give you an example. Maybe everyone who's a professional runner has been told since they started running, the Nike shoe is the better one, right? So if professional runners are under the impression Nike's better, and then Nike's the shoe A being tested, well, they'll go, oh, well, I like that shoe. I know that's the faster shoe. They'll pick that, but we won't be able to tell that's actually the faster shoe, because the faster people who are professionals have been told to use that shoe. So we don't really know if it's the shoe or the fact that they just come in with that bias thinking it's the shoe. And then when we look at the results, we go, oh, look, the Nike one's faster. But it's really because all the fast people chose it for some other reason other than it's actually maybe the faster shoe. Maybe it's been advertised to them that way and that the shoe really isn't that good, but they themselves, being the faster runners, make it better. So why randomize? Well, randomize reduces the effect of other variables we can't control for by evening out those differences as best as we can. So there could be other factors, and by randomizing, because we can't control for every factor, we can't know everything. We're not gods. So basically, by randomizing, we're evening out the things that we can't possibly control for as best as we can. And like I had said, if people choose their shoe, there may be another reason behind why they're choosing the shoe that is also related to why they're fast or why they're slow. All right. So we don't want other things. We don't want them choosing. Them choosing can be bad because they might choose for a reason that we're not aware of that affects both variables at the same time. Randomizing is the best way to get rid of any kind of bias that may appear within the people. All right. And then part C, explain how the design of the experiment will address replication. What is the benefit of the replication? So replication is just doing the thing over and over and over again. There are two types of replications. There's replication within the experiment. That just means doing it to a lot of subjects. There's also the ability to replicate the experiment outside of itself, meaning if I did the experiment and I gave you the directions, you could do the experiment again. Now, they're not talking about you doing the experiment again. So they're talking about within the design. So they're talking about the fact that they did it to 100 different people, right? If I just gave one person shoe A and another person shoe B, well, with just a sample of one person can vary a lot. So one person, even 2, 5 people isn't really enough to get a good result. But they went up to 100 people, right? 50 of one and 50 of the other. The more people you pick, the better, right? So when the answer to the first part, how does this design of experiment address replication? Well, basically, it does it by giving the experiment to many different people, right? It replicates it 100 times, essentially. What's the benefit of that? Well, that's what I was just talking about. What's the benefit of the replication? Well, if you just have like I said, one person do it, you might get lucky and get a really fast runner or a really slow runner and make one shoe look better than the other. Basically, you're trying to estimate the population, right? So when you go shoe A is better than shoe B, if you make that statement, what you're saying in general is that of everybody who uses this, shoe A will generally benefit everybody overall. So what you want is that if the shoe was truly better, it would make the population mean go up. It would mean that everybody, if you had everybody use shoe A, that shoe A would end up with the better times than shoe B. So the benefit of replication is the more people that you have do it, the more likely you are to be closer to the population mean. So if you pick one person, that one person can vary a lot. But if you do 50 people, a group of 50 people can't vary that much from the population mean, right? So if I know a certain group's going to run the mile in, on average 7 minutes, if I pick 50 people, it's very difficult for that group of 50 to vary very much from 7 minutes. One person can vary a lot from 7 minutes. So basically, the benefit is being able to get a more accurate estimate of the population mean, because the more people sampled, the better the group mean is likely to be as an estimate of the population mean. And remember, the bigger the sample mean, the less the standard deviation, and the less we're actually varying from what its effect on the entire population would be. All right? So that replication is basically making us, the bigger our sample, the closer we are to that sample representing the population mean. So 50 people, if I see 50 people doing a better job with shoe A than shoe B, that's more convincing than one person or 2 people. In fact, if I did 1,000 people, the more you do, the more likely it is that it's working, right? 1,000 people did better with shoe A overall than shoe B. That would be very convincing evidence that shoe A was better for everybody, all right? So those are the answers as I came up with them. let's look at the point values and what they wanted you to say and how they graded it out. So part A, which was about the blocking, criteria number one was to say that blocking accounts for a known source of variation or / confounding variable. So we're blocking because there is a known source of variation. We have different type levels of runner, right? We have a fast runner and a medium or slow runner. So we block because we don't want that difference affecting the shoe. Also, blocking makes comparisons better. So sorry about my bad handwriting. It looks like Bezer or something. So blocking makes the comparison better. The reason we're doing is because we don't want the other variable getting in the way, and it improves our ability to compare shoe A to shoe B. If we don't do this, someone could argue, well, maybe it looks like shoe A is better, but all the fast runners got shoe A, right? Then someone could make that argument. So if we blocked, we get rid of someone's complaint and go, hey, no, this is a good comparison, all right? So you have to mention, the variation, the fact that one source is going to affect another. You could say something about confounding variable, and that it improves what we're trying to do. If you mention both things in some way, you get the E, 1 out of 2 is the P, and then otherwise you get the I. Part B was about the replication. Part B was, let me check, the randomization. Okay. How quickly I forget. So B is about the randomization. So what'd you have to say? Well, randomizing reduces other sources of variation. That's what I basically said, that we're randomizing because we can't control for everything, and randomizing helps basically even out other sources of variation. So they did allow you to say something about it being required for cause and effect conclusions, which I thought was a weird thing to say. But if you did mention, randomizing is necessary in an experiment because it lets you prove things, they took that. But I think this is the better answer, and that was the primary answer. So you have to say something about randomizing, evening out other variation of other things that you can't control for, and the thing about self-selection, that self-selection could introduce another confounding variable, right? If you let them pick, they may pick for a reason that you don't know about, but the reason they pick could also be a reason why they're faster, all right? And that's where I tried to use the Nike example, right? Like there might be a reason why they're picking, and it may also have to do with why they're fast or slow. So if you have both categories hit, you get an E, 1 out of 2 is a P, and an I otherwise. And then the last one, that's about the replication. So identifying the replication, saying something about 100 runners were used, or 50 in every group, or that they did it to many people, that's the replication component. And then the reason why, basically replication helps home in on the values to get a reasonable measurement of if there's a difference or not. So basically, if you use 1 or 2 people, the difference is not significant. If you use a lot of people, you show that, look, if there is a difference, it is significant because the difference is being seen in a lot of people, not just one person who can vary a lot, but 1,000 people can't vary, a lot at all in their average. Here they have 50 people in each group, or 100 people overall, and it's hard for a group of 100 to vary that much from the population mean, right? They might vary a little bit, but overall, most of the time, you're going to be pretty close to that population mean. So when you see a difference in the two shoes, this replication, by doing it to a lot of people, it helps you show that if there is a difference, it's likely a significant difference, right? 100 people were faster in shoe A than they were in shoe B. That's pretty convincing. It's not so convincing if 2 people were faster with shoe A than shoe B, because you might be like, well, you got lucky with those 2. It's hard to get lucky with 100, right? Okay, so the points in the end, just like most of these other ones, and I have to keep adding this thing in because I forgot to write it on half my keys. The 3 E's is the 4, the EEP is the 3, kind of 2 hits or 3 hits here. This is like the EEI, the EPP, PPP, and EPI. These are all 2 points. EII and PPI are 1, and then otherwise you get the 0. So like the PII doesn't get you anything, and III never gets you anything. III. All right, so That ends this video. Be on the lookout for AP Practice Problem 3's explanation. Bye.